Hey, welcome back. Steve Basic Architect. Yeah, we're back at our Passive House 11 series. For those of you that haven't been watching all of them, and this might be your first video of the series that you catch, this is a house that we designed in 2009. We built it in 10 and we certified it in 2011 as a certified passive house here in the United States. At the time, I think it was like the fourth or fifth passive house in the country. So it was definitely in its infancy, almost 14 years ago. Well, right around 14 years ago, we designed this house. And it's in Climate Zone 5. It's down on the Cape in New England. So it's you're not going to find it. It's in a pretty well hidden down there. If you found it, it would definitely be by chance. So, anyways, today we're going to go more towards a structural science than the building science, but there is like some of the decisions we made for building science purposes aided us in the structural integrity here. Like I said, it's a Climate Zone 5. This is on the coast, right? So it is in the worst wind zone that we can get. It's the high wind zone, so it has to be designed appropriately for lateral loads, right? Lateral loads are when the wind comes in and blows on the house here, right? A couple things want to happen. It wants to lift the house off the foundation here and rotate it, but this wall also wants to cave in. So we have to solve for a number of those things, and basically developing shear resistance is what we're going to be talking about today. So quick look at the floor plan. You can see it's really not that big of a house. So we have shear here, we have shear here, we have a little wall there, so that direction is certainly taken care of. In this direction, we have that wall and that wall. We have some wall here, and then of course we have that wall there. In this direction, we also had that wall and that wall to help us. Like I said, it's really not this very large house. We do have a significant amount of glass on the front here though, and then you can see up above we have a lot of glass, which, the minute you start diminishing the wall, then we start having some issues with shear resistance. So here, this you really can't count, that you really can't count. So we have that and we have that. This direction here, we're well taken care of because we have a lot of wall there, we have a lot of wall here, and of course across the back we have a lot of wall, and then inside we have that wall, and inside we have that wall. So we're pretty well taken care of. The question is really like what's happening out here and out in here for shear, right? And it's not when the wind blows in this direction, it's when the wind blows in that direction, because we don't have a whole lot of wall, or likewise when the wind blows in that direction. So how do we solve for it? This is an elevation of the front, and it's a shear wall elevation, not a building elevation, although it's kind of the building elevation superimposed on this framework below of the shear wall. So let's run through some pieces on this. You'll see this is where the floor comes in. That's our floor frame above. This is our top of foundation there. You can see we have our anchor bolts called out, every one of the locations, but more importantly, we have all of our window openings, and we actually have them all labeled here in square foot, how much glass area, gross wall area, almost 700 feet. The net is 475 because 32% of this wall is glass. Given it's a passive house, we want to put a lot of glass in, climate zone 5, heating dominated climate. We want to let the sun shine in because the sun brings heating energy. Heating energy from the sun is free. Free energy is better than purchasing energy. So if we're trying to knock down our energy efficiency, then we try and use up as much of the free stuff and then supplement it with the stuff we pay for. I know you knew all that, but I figured I was obligated to run through it anyway. So, continuing on, we have our windows. We have the second floor up here. And like I said, right, there's areas of success and areas of not success. Like this, that's not. There's nothing there that's really going to help us. Because when you deal with shear, and for all the structural engineers out there that might watch this video, or people that are certainly smarter than me in structural, I know enough to be dangerous, right? I don't claim to be a structural engineer. I didn't do the calculations for this. I worked with our structural engineer, but I have a sense of what we were trying to accomplish and what works and what doesn't work, right? So when I say not, what I'm really talking about is there's this thing called an aspect ratio, right? And the aspect ratio suggests that taller, slender things, so if I build a wall that is 9 foot tall, but only 1 foot wide, the ability to overturn that wall, there's not a whole lot of resistance laterally. If I apply a load up here, that thing goes over pretty darn quick, pretty darn easy. But if I build a 9 foot wall that is 8 foot wide, right? So the aspect ratio is different. It's 9 to 8 instead of 9 to 1. And I apply a load here. This really isn't moving, right? Because I have enough of anchors, right? Everything here wants to rotate on that point, like here. Well, I don't have a whole lot here, right? So, probably an easy way to understand it is I'm roughly 6'6" tall. If I stand up and people try and push me over, it takes a lot more energy for me to be pushed over standing up. But if I sit my butt on the ground and you come over and I cut my height from 6'6" to say 3'8", whatever height I am when I'm sitting on the ground, and you come and try and push me over, it takes a lot less energy for me because I offer a lot more resistance due to an improved aspect ratio, right? I'm not as tall and slender to get pushed over when I'm sitting on the ground as opposed to standing on the ground. So it's the same here. And likewise, if we took this 9 foot wall and we only made it 2 feet tall and made it 2 to 1, then I apply a load here, then it's going to be a lot harder to overturn that smaller wall. And not only that, but I only have 2 feet to accumulate the force. Here I have 9 feet to accumulate the force, right? So it's a bigger billboard to capture that wind. So that being said, these are not spaces because there's not really a whole lot we can do there. You know, for an 8 foot wall, 8 or 9 foot wall, you need to start somewhere at a 2 foot wall, right? It's no surprise that garages are usually the garage door plus about 2 or 3 feet on each side because it's called a garage door portal. The aspect ratio of those side walls have to be a minimum of 2 feet by code, unless it gets engineered, to basically withstand the shear lateral forces that come into it due to its aspect ratio. So anyways, looking at this, you can see also, these in green, you can see we've pretty much laid out every panel And when I say every panel, this is the shear panel, or in this case here, it's right here. Right? So that is one panel of zip. This is another panel of zip. And so in this one, we're using continuous sheathing. Basically, where we don't have windows, we blanket it with OSB. The structural engineer runs through the calculations and says, okay, we don't have that much window. It's a successful wall system, which is the other 3 walls on this house. In this case here, it was, you know what? We're kind of on the cusp of not being successful. We have to add some stuff. So by virtue of having a double wall where we have a 2x6 and a 2x4 wall on the inside with drywall and sheathing here, what we did was we came up with the idea in that cavity we can do some 2x lateral struts and put them on the diagonal. They're not lead-in bracing because they don't have to be let in the wall. We have, you know, upwards of 9, we have like a 4-inch cavity here to deal with. So we can just put the 2x4s in there. So that's what you're seeing here, right? We have a 2x4 there, we have a 2x4 there, we have a 2x4 there. And then consequently upstairs we have one there, we have that one, we have that one, and we have this one. Notice on here we actually call out the OSB sheathing and we call out the nail spacing. So around the perimeter it's 3 inches on center. Through the field of the wall it's 6 inches on center, and the nails are called out as 8D nails. And you know, our shear diagrams, actually we've improved them since this, and we actually call out the diameter of the nail. I believe it's 0.131. But anyways, we want to call that out because the nailing pattern makes a difference, right? If I put 20 nails in or 40 nails, the 40 nails is most likely stronger. Now, one of the problems with that is let's say I don't put in 40, I put in 80 nails. Well, the problem is there's a tipping point where you deteriorate and you put in so many nails that when the wind blows, the OSB panel just simply tears like a zipper because there's so many penetrations. There's not enough resistance in the panel to overcome the force of simply tearing along the fastener line. So getting that spacing right is critical, right? And having these 2x4s in between the windows. And the other thing to point out is, notice, and this came from the structural engineer, anywhere that 2x4 came down, we have an anchor bolt at that location, and it's intentional, right? So, and they're actually added in on the dimensions of the diagram there, so that when the wind blows, not only is this strut doing some of that work in bracing, right? And it's the same as if I'm standing tall, 6'6", and someone tries to push on me. Well, if I'm just standing there, I'm a little easier. But if I take a 2x and have a little back panel and I run that 2x diagonally, right? So I'm standing here on the ground and you're trying to push me, well, I might go right over. But if we extend that ground and then I put a panel back here with a strut and you try and push me, it's a lot harder to push me over because you have to not only overcome me, but you have to overcome that strut. And that's what we're doing here. We're putting those struts in. Now, as the wind blows and this thing wants to overturn, it also wants to tear out here. Well, because that strut is nailed to the double bottom plate or double mud sill, that double mud sill is anchored right at that location. So we get some nice continuity and in our structural integrity where that strut meets that mud sill, and then we have those anchors. And so the beauty of that double stud wall was that we were able to, for the cost of, I don't know, maybe a dozen, 15 2x4s, satisfy all of our high wind shear requirements, in addition to using the continuous sheathing method that we used for the project here. And I drew all of these drawings. You know, you look at this one's real easy in that, you know, we have the strut here, we have the strut there, strut there, strut there, but look at this. I mean, we have a ton of wall that is working in our favor. Notice though, we still have our anchor bolts where those struts meet there. We have minimal windows here. So like I said, the sides and the back wall, we had our percentage of windows, you know, the front was upwards of what, 33. We're at 8% here, right? So it's a quarter of the amount of glazing that we had on the front of the wall. And we certainly have a lot more wall area here, the net wall area. 92% of it is a sheathed wall, so it's really strong in that direction. So remember this wall, we have a window here and we have our door there because, and we have our anchor bolts dimensioned out to those struts. And like the front one, you can see we have our nailing pattern. We have all of our panels laid out. And like I said, I do all these drawings and then I pass them on to the structural engineer. He marks them up, and or he'll give me a quick sketch and I'll draw it up. And you know, for young architects out there watching, the reason I do that is not because I'm trying to build the drawing set or that, but I really strive to understand everything there is to putting this building together. And so working with the structural engineer and having him do a sketch and me doing the drawing helps me really understand what our goals are and the why of a lot of his decisions. So that enhances my education. So window and door, a couple windows up above. We won't see those in the next photo, but here is that window or that door. Remember, we did a raised floor and here's that window. But here is that strut. And notice it's on the inside of the wall. And here's the other one there. And you can't see it, but there is an anchor bolt there. And there is an anchor bolt there. And you can see how that all comes together. And that stuff is basically framed on the inside of that 2x6 wall. And then it's just basically nailed at each one of the studs. So that now you have somewhat composite action all the way through here, and this blocking here is to capture the panels, right? So we have our panels here. So our panels are now working in concert with those diagonal struts. And here you can see these were just a couple anchor bolt shots. We have to have anchor bolts within 12 inches of the corner. And you can see here, we used 3-inch washers, which we have to use in the high wind areas. Just because if you use a smaller washer here, right, you have the risk of when the wind blows, this wanting to rotate up and basically just tear out around that little washer. Having that 3-inch washer makes it much harder for that 2x6 to tear out and deform as this building wants to lift off of the foundation. And here you can see, here's our strut coming in. We have our nails, that's going in, and we have our anchor bolt, and then this is just, that's our standard anchor bolt that's on 32-inch center. And this is our custom anchor bolt here, right, where that strut is coming in on that. So and here you can see it, you know, this is it on the inside of the wall, and you can see all the nails there. So it basically just gets nailed off at all of these locations. And then we'll frame that 2x4 wall on the inside of that to complete it. So anyways, there you have it. I'm Steve Baczek, Architect. This is the Vibe board. If you're looking for more, you can certainly find me on the Build Show Network. I put up videos there every week. Every other week it's 2 videos, so you get 6 videos a month of stuff I'm doing that month. And the categories differ. Sometimes I'm talking about a bath vanity. Sometimes I'm talking about the way we run mechanicals in the basement. Other times we're talking about a rain screen or an air sealing detail. So it's a kind of potpourri of building on the Build Show. So go check it out. A couple hundred videos, all free to watch. Tell all your friends, go over there. You know, people are always asking, hey, where do I go to find out more about this or that and this and that? Hey, start at the Build Show. If you're still looking for more, you can find me on Instagram, LinkedIn, Facebook, TikTok, and of course, you found me here on YouTube. All right? Make sure you subscribe. Smash that subscribe button. And most of all, tell all your friends. Tell all your friends. Go check out Steve. Passive House 11 series. Yeah, you watched it here. So hopefully you enjoyed that. That was actually a really interesting part. I learned a lot about wind bracing and such from the structural engineer when we did that project and his solutions that he posed there. So it's always great working with these people and you know, trying to find out better ways to solve our problems. So anyways, like I said, hopefully you enjoyed that. Until next time, on with our buildings.